Okay, I think I'm recording. Yes. So this is just a quick video on how to generate the bill of materials information for the NanoRacks. So there is an example bill of materials on the drive in the ADCS folder under CubeSpace ADCS called CubeSpace BOM. And so this is a NanoRacks approved bill of materials, as well as there is another example bill of materials that the CSA has provided that I will link on Slack with this video. But this gives you an idea of what they're looking for. So it's not like you don't need to write down that you've got, 100 MLCCs with this part number. They care about surface area and material. And mass, if the mass is, I guess, easy to compute or has a significant mass. So this is for the Cube Computer ADCS. You can see that they've got the high temp R44, that's for the PCB. They've got a PCB solder mask on here as well, and then they've got like a crystal. They're just calling it ceramic. They've got integrated circuits, and they're just calling these integrated circuits made out of moldy epoxy resin, thermosetting polymer, or thermoplastic. So you kind of get the idea. You're just trying to group things into common materials, and then you're just figuring out what the surface area of that is. Now obviously, if you look at an Altium project, and I'll just open up the old PCDM here, there's not really an easy way to get that information out of there, but there's a way that you can get the information relatively easy. So I'll show you how to do that really quick. So if you open up your PCB, if you go to the properties panel, and I will just, okay, Altium, let's just freeze, shall we? Right while I'm recording. Ideal. So this is the PCB. If you open up the properties panel, you'll see that there's this board information tab here. And this actually gives you a little number, which is called components area. So Altium does actually have a way of calculating component surface area, as a way of calculating the component height as well. So depending on how you made your components, you should be able to pull that data off of it without too much trouble. So if I open up like a fuse here, you'll see that there's an area, 10.58 square millimeters, and there's also a height assigned to it. So if you're making these components using the IPC compliant footprint wizard, these numbers are populated automatically. And if you made the footprint manually, like this connector, the height is what you manually put in when you're making the footprint library. So you should have heights in all of these, and if you don't, you're in for a bad time. But anyway, if you do have heights, then Altium either generates this number through the IPC compliant footprint wizard or calculates it automatically. And how it calculates it is it just basically looks at the footprint, and then this gray box, when you select the footprint, it just grabs the X and Y of that gray box. So it's not exactly accurate because, as you can see on the top assembly layer, the footprint, the component is actually this big, but Altium is saying that the component is actually this big because it's the whole footprint. So it's not totally accurate, but it's good enough, and it'll save you a bunch of time when generating the BOM to use this. So how do you get this data? Well, the easy way is you open up the PCB list panel, and that's accessed by just going to PCB list here. And if for whatever reason this isn't popping up, you can just go into preferences and go system view and just hit reset view, and that'll basically reset all of the panels, because what happens with Altium is a lot of these panels, when you open them, if you don't close them but you minimize them, it minimizes them to 1 pixel, and then you can't actually close it or maximize it. So an easy way, a lot of times if you're trying to open a panel and the panel isn't opening anywhere, just reset your view and then reopen the panel again. So anyway, if you open up this PCB list, I'll just bring this way out, you can see that this PCB list with no queries at all gives you basically a list of all the items or objects in here. So it's got tracks, pads, text, everything in here. And you can use like the query functionality to pull data from here, but you don't even need to do this. Just scroll through all of your stuff until you get to component, which is usually at the very bottom here. So these are all my components here. And you'll see that each component has a height assigned to it. And if you go over, you'll see that each component also, the very last column, there's a lot, I'm just going to scroll this. The very last column, whoops, okay, let's try that again. The very last column also has the square millimeter area assigned to it as well, which is the data from each component. So the really easy way of doing this is just to open up a Google Sheets, which I've got one right here, EPS v1 safety data package bomb. And so what I've done is got this raw data column, and all I've done is I've just copied the component tab. So I've literally just gone here and I've just grabbed the component designator name from this column here, and I've just copied this all the way down. So all my components, I've just grabbed this. There's a lot of components in here. I've just grabbed this. You know, you can literally just copy this and then paste it directly into the sheet. And then you want to do the same thing for the height column and then the area column. And that's all you're grabbing from the Altium project. And once you've grabbed it, what you can do is you can then create a 2D surface area. And this is basically because you're copying it as 1.8 square .mm. This is not a normal unit designator, so Google Sheets has no way of actually ripping the 1.8 out of this. So you have to just split the string, separate the number out of the unit, out of the text, I should say. And there's a couple different ways of doing this. The way I did it was I just concatenated at the first decimal, or I split it at the first decimal number thing, and then just concatenated it, and it leaves you a column of just the second period. And there's a way cleaner way of doing this, but I don't feel like figuring it out. But anyway, you can just hide this column, it doesn't really matter. This gives you then just the number, and then you can then calculate the 3D surface area of the object, which is what NanoRacks actually cares about, by basically taking this number and assuming that the component is a 3D cube and not a cuboid. Most of these components aren't cubes, they are cuboids. They're, you know, rectangulars that are 3D or something like that. They're not cubes, but in order to actually figure out what this actual surface area is, there's no way to do that from just the height and then the 2D surface area. So you just assume it's a cube, and then you just use this formula, use the height, the surface area, and then it gives you the 3D surface area in millimeters squared here. And then you can just copy this sheet and use it for yourself. And then all you're doing is you're just applying a filter to it, you know, by just going data, turn on a filter, and then you can then just sort by component. And then because your components all start with a common designator, so capacitors are all C, diodes are all D, etc., you can then just start grouping all these things together. So all of your capacitor surface area, assuming you're using all MLCCs, you can go like this, and then you have your sum down here, 1493. So then you can go over to your BOM and go ceramic capacitors. My ceramic capacitors are all MLCCs, X7R, X5R, or COG and PO type. And then I've just populated in the 2D surface area and the 3D surface area some of all those components. And then you can just kind of go through and go, okay, well, diodes. These are all my diodes here. You know, so I've got 521 square millimeters of diodes. And you don't have to be super accurate with this. Like, most of these diodes are not LEDs, but there are some LEDs in here. So I'm just saying that it's all just one diode, and it's just using the classic SOD FL, I think the package is. SOD FL? Yeah, SOD flat lead, like the classic diode package. And then I'm just saying it's just an epoxy molded case, and that's the sum of the area. Even if some of them are LEDs, which don't fit into that, it's close enough. And then etc. Like PTC reset out fuses, Where you can, try and get data sheets and try and find some of the materials data for this. So the PTC reset fuse is actually able to find out that the case is mostly fluoropolymer, carbon black, foil, and epoxy. Other things like connectors, you can find out that it's a black liquor-stick polymer thermoplastic with an AU plated contact. Other times for ceramic capacitors, all you're going to be able to find out is just the dielectric material. Things like resistors, you're just going to basically find out that it's just a thick film or a thin film or whatever. You're not going to actually find solid material data on most of those things. So that's what you want to do for electronics. And then the PCB solder mask, this is just a really easy calculation to figure out the 2D surface area of that. And then the PCB core is really just the edges of the PCB because everything else is covered. You kind of get the idea. It doesn't have to be super accurate. It's just to kind of get an idea of what are the main kind of exposed surface areas, or what are the main surface areas that are exposed to a vacuum, and what materials what materials are on those surface areas. And then this is what you do for electronics basically. And then for everything else, you can just open up SolidWorks and just calculate surface areas of like metal brackets and whatnot. So every team needs to make one of these, and that's probably the easiest way of doing it. That gets us a semi-accurate number without manually going through and trying to calculate all this stuff by hand or guessing at it. So yeah, that's the video. 10 minutes long, way too long, but we're good.